to share more insights, ideas, and expertise with you. Now I request Dr. L. Meenakshi Sundaram, Associate Professor of Mathematics, to welcome the gathering. Sir, please.
Good afternoon to all. On behalf of Mathematics Department, I welcome to the fifth day faculty development program on exploring new horizons in mathematical research. First, I welcome our resource person, Dr.K.Sumathi, Head Department of Mathematics, PSGR Krishnammal College for Women, Coimbatore. She is going to talk about mathematical modeling. I welcome our head, Dr. Deva Manohan, and the organizing secretaries and our department colleagues. Finally, I wholeheartedly welcome all the faculty participants and research scholars from various colleges and various states. Once again, I welcome all of you. Thank you. Thank you.
Thank you, sir, for your warm welcome. Now I request Dr. Jackson to introduce our chief guest.
So good afternoon to one and all present here. A renowned resource person for the Day 5 program of our faculty development program on exploring new horizons in mathematical research, Dr. K.Sumathi ma'am, Head and Associate Professor of UG Department of Mathematics, aided stream, PSGR Krishnammal College for Women, Coimbatore. She is a distinguished academic with extensive experience in the field of mathematics, nearly 30 years experience, contributing significantly to both teaching and research. Under her guidance, 35 scholars have completed their MPhil degree, 11 have completed their PhD degree, and 4 is undergoing the process of PhD. Under her leadership, the department has tried fostering a robust academic environment that encourages both faculty and the students to excel in their respective fields. Dr. Sumathi is known for her commitment to the academic excellence and her dedication to the holistic development of her students. Her expertise and guidance have been instrumental in shaping the careers of many young mathematicians. On her academic path, she has published nearly 60 research papers in the reputed international and Scopus indexed journals. She also having 8 seminar proceedings. However, she has published 1 book as an author and 4 books as a co-author. She has she is serving editor for 2 journals and review member for in the editorial board of 7 journals. And not only in academic path, she has more administrative responsibilities in her institution. Served as a UGC Stride Coordinator for the year 2022-23, UGC Paramash Coordinator for the year 19 to 20, IQSC Coordinator for the year 2016 to 2019, and NCC Officer from the year 2002 2008. She has been the resource person for the workshop and faculty development program is more than 20, and seminar and conferences more than 20. Such a renowned resource person, committed resource person, today we have amidst us. So on behalf of our department and institution, welcome you, ma'am, and our wholehearted thanks for accepting our invitation to be the resource person for this 6 days faculty development program. Thank you.
Thank you, sir, for the brief introduction. Dear ma'am, we are so happy to have you with us today. Kindly take over the session, ma'am.
Thank you, ma'am.
Thank you, ma'am.
A very good afternoon to everyone present here. And my special thanks goes to Dr. Jackson, who has invited me for this session. And it has always been a pleasure to work with V.O.C. College. I have been looking around for the past 10 years that many programs are being organized under the wing of the mathematics department, V.O.C. College, and I'm glad that they are our knowledge partners. So with this note, I will let me enter into the mathematical modeling lecture. First, let me define what is a model. A miniature representation of something. It is a pattern of something to be made and an example of imitation or emulation. In that case, what is a mathematical model? It is just a mathematical representation of a system used to make predictions and provide insight about a real world scenario. And mathematical modeling is the process of constructing, simulating, and evaluating mathematical models. So, what is the difference between a mathematical model and a mathematical problem? If we look into it, suppose if I give you x plus y is equal to 5 and x plus 3y is equal to 45, and if I ask you to solve the problem, what is the value of x and y, then that is just a mathematical problem. Instead, if I say you the present age of a father and a son is 25, and after 5 years, the age of the son will be one third of the age of the father. If I tell you, again, you will come back to the same kind of system of equations involving x and y. But now, after solving that, after finding the value for x and y, we will see that the x is to be interpreted as the age of the son and y has to be interpreted as the age of the father. So instead of having just two equations involving two unknowns, now those equations and the unknowns, they are representing a biological situation where a father and a son is involved. Hence, that is the main difference between a mathematical model and a mathematical problem. A mathematical problem, which is representing a real life scenario, that is a mathematical model. So, why do we need a mathematical model? Or mathematical modeling, is it necessary? What is the need for it? I would like to show you some simple situations requiring mathematical models. Now, suppose if I want to find out the height of a tower without climbing on the tower, then I have to use a mathematical expression. I have to use angles and distances, and I have to find out the height of a tower. In the same manner, suppose if I want to find out what is the mass of a Earth or mass of a planet, if we are going to find out what is the mass, there is no scale which will give you what is the mass of the Earth and where you can weigh the planet. So in those cases, I would like to go in only for a mathematical model. Similarly, let me find out the temperature of the sun. If I'm asking you to find out the temperature of the sun, do you have any device which will measure the temperature of the sun? The answer is no. So in those cases also we require some mathematical models. Now suppose if I want to find out what is the radius of the earth, then there also we go with the mathematical modeling. So these are all the very few situations where mathematical models are the only possible way to find out a solution. Then is that the only places celestial objects and which are somewhat alienated from our day-to-day life? No. Mathematics is applicable everywhere. Mathematics is applicable in market, cricket, health and satellite, etc. So the unlimited applications of mathematics involves stock market, cricket, health sector, satellite and space, communication, insurance sector, software industries, security systems, ecology, atmosphere, and robotic designs. And certain situations can be modeled only using mathematical models. For example, now I have given you the fire accident at an oil depot at Jaipur, which happened in the year 2009, 20th October. Now you can see here how many smoke is going into it and how it is going to pollute the entire environment. And what is the impact of this pollutant on the environmental? Is there any measurement that can be done except a mathematical model? Only mathematical model can predict what is the damage that can be done because of this kind of accident. Similarly, to measure industrial pollution and vehicular traffic. Suppose if the traffic police wants to find out a place where a signal has to be put. Right? Now, you can see how dense the traffic is here. In this place, is it possible to stop the entire traffic for one day and check which place is required to keep the signal to check the optimality of the decision? Definitely no. So, in these cases, graph theory comes into help. So, to go on the lighter vein, I'll just give you what can be modeled. Everything can be modeled. Anything can be modeled. See, for example, you just consider this. You consider this pizza. Everybody we know what is a pizza, right? Now, I'll just give this as a mathematical statement. Write the expression for the volume of a thick crust pizza with height A and radius Z. See, if this pizza is considered to be a cylindrical object, right? If it is cylindrical object, what is the volume of that cylinder? All of us we know. It is pi r square h. Now, pi into radius square into height. That is the formula for the volume. Now, what is this radius? I have said the pizza will be taken as the radius z. So, it is pi z, and then the height, I'm taking it as A. So A I'm adding. So that makes it pi into Z into Z into A. That is pizza. The word pizza itself can be modeled using a mathematical expression. And another most recreational example, if I go into it, it is in everybody's mobile, a game which is called 2048. It is a single player puzzle game where we will be playing with tiles, right? And this game was created in March 2014 by a 19-year-old Italian web developer, in which the objective is to slide numbered tiles on a grid to combine them and tile with the number 2048. So here what we are going to do is actually anybody with a children who is raising talking Tom, they will be knowing of this game 2048. So all the small children, they will be playing this game, and how systematically we can play this game and how we can win using a mathematical concept. Actually, in case if somebody of some of you or do not know what is this game, then we will go for this. See here, the tiles will appear at random. 2 and 4s will appear. And the same number tiles you have to add. 2 plus 2 will give you 4. And again, that 4 can be added only to another tile which is having the number 4. When you are joining the tile with number 4 and 4, it will bring 8. And that 8 can be clubbed only with another 8, which is here, right? And 8 plus 8 will give you 16, and that 16 can be clubbed only here. So this is the way we go with it. So 2048 is played on a gray 4 by 4 grid. See with the number tiles, how we are sliding, you can just see in this zip file. 2 plus 2 will constitute 4, and 16 plus 16 is going to give you 3. Like that, it will keep moving. And every turn, a new tile will randomly appear in an empty spot on the board with a value of either 2 or 4. The tiles can slide as far as possible in the chosen direction until they are stopped by either another tile or the edge of the grid. If two tiles of the same number collide while moving, they will merge into a tile with the total value of the two tiles that collided. That is, 2 can be added with another 2. 4 can be added with another 4. Whereas 2 cannot be added with a 4 or 8 or any other number. And the resulting tile cannot merge with another tile again in the same move. So higher scoring tiles emit a soft glow. This is the way the game is placed in your Android mobiles, right? Now I have given you a completed game of 2048. This 2048 you can see at the bottom right corner where here it is 2048. The screen is visible.
Yes, ma'am.
Okay, thank you. So here, this one simple game, it is having lot of mathematical concepts. It is using induction, isomorphism, geometric sums, topology, probability, and optimization. I'm not going to give you the minute details of all these exercises, but only thing is, what you can see is all the tiles, mathematical induction concept alone I will explain. All tiles are powers of 2. That is 2, 4, 8, 16 only will be appearing on the screen. Assuming that at some stage all tiles are powers of 2, then at the next stage all tiles will still be powers of 2. At first, the only tile on the grid is the initial 2s or initial 4s we start with. And 2 and 4 are powers of 2. More precisely, if you are adding this, again the resulting tiles, see only 4 can be added with 4. 2 can be added with 2. And like this, if you keep on going, then everywhere you will get only powers of 2. So how you have to complete this game? To complete this game, you have to use the geometric series. So your sum must be 2 plus 2 square plus 2 cube plus 2 power 4 plus etc. 2 power n or n minus 1, whatever it is, you can take. And the total sum, it must be equated to 2048 or even the higher numbers. And that is the crux of this game. And all the numbers, it has to be following the topological paths. So the way you have to add your numbers, it should either be in one of these shapes that are shown in the screen, right? So if you can do like that, then always you can complete the game, not only to 2048, you can even cross further to 4096, then 8192, then next number, 16384 and 32,768, and ultimately you can reach even 1,31,072. So here the only two concepts are the hypergeometric series concept and the way you are connecting those powers of 2 using a continuous path, topological path. So why do we go for a mathematical modeling? It is the fundamental and quantitative way to understand and analyze complex systems and phenomena. And is it a replacement for theory and experiments? If it is asked, I would say it is no. It is not a replacement for theory or experiment. It is only a complement to theory and experiments. And sometimes this mathematical modeling, it integrates both theory and experiments. And it is very commonly used in computational physics, chemistry, mechanics, material science, biology, and other fields. So mathematical modeling, it seeks to gain an understanding of science through the use of mathematical models on computers. That is why this mathematical modeling is always, it is representing a real life situation or a natural phenomena where the number of variables or the number of unknowns are more. And the problem may not be mathematically tractable. When the problem is not mathematically tractable, then automatically we have to go in for the help of the computer software. And in that case, Mathematics, standalone mathematics can never represent any of the natural systems or real life systems. So mathematics has to become interdisciplinary or transdisciplinary. So it has to combine either with another science or computer science or even arts, humanities, English literature, whatever it is. But mathematics should go hand in hand with another discipline, and with the help of computer science, you can come out with a very good mathematical model to represent any real life situation. Hence, mathematical modeling, it involves teamwork. And mathematical modeling, as I said earlier, it can only complement, but it does not replace theory and experimentation in scientific research. So mathematical modeling, where and all we can use. It does emerge as a very powerful and indispensable tool for studying a variety of problems in scientific research, product and process development, and manufacturing in seismology, climate modeling, economics, environment, material research, drug design, manufacturing, medicine, and biology. In case if you go for a combined research with either an economist or with a biologist, definitely you will win many national and international awards. That is the power of the clubbing of this mathematics with other disciplines. So I would like to bring to your notice a very, very old mathematical model. When I say mathematical modeling, it is not a new field or it is not a new concept. And always this mathematical equations, mathematical concepts have been used to come out with many innovative research ideas and many innovative developments. And the oldest one, if you can say, it is measuring the surface of the earth. Eratosthenes, he was a Greek geographer who lived between before Christ, 276 and 195. He is best known for his accurate calculation of Earth's circumference, and he started a mathematical system known as Eratosthenes sieve. Actually, it is for determining the prime numbers. Every one of us, we are associated with this Eratosthenes sieve, because we will be writing all the numbers 1, 2, 3, 4, etc. up to 100, 200, whatever the upper part we have, we will be writing it, and we will be circling 1. Then we will circle 2 and we will cancel off all the multiples of 2. Then we will circle 3 and we will cancel all the multiples of 3. And 4 already would have been cancelled. So next leftover number is 5. We will circle 5 and we keep going. So this is the way we keep going. And after completing this, all the numbers which we have struck, those numbers are composite numbers, and those numbers which are left circled, those are prime numbers. So that is a contribution of Eratosthenes, and he has also found out the radius of the earth some very many years ago, that is 2076 BC and now 195 BC. Between that year, he has done that, and he has also determined the inclination of the ecliptic to the celestial equator and how that has been done. See, you can see like this. He has served as a chief librarian at the museum at Alexandria, Egypt. His method of measuring the Earth's circumference is an example of mathematical modeling. So what we have done is, one day, this Eratosthenes, he was sitting there in Alexandria, and he was uh, listening to somebody else who were traveling along the city Alexandria. They were talking among themselves, and they were telling each other that in Sion, which is nearly 800 kilometers away, there the sun rays are directly falling on their head. And in Alexandria, the sun rays, they are falling at a degree of 7.2 degrees. This was the concept they were, this was some information they were discussing among themselves, and they were walking by. And Eratosthenes was listening to this, and he was thinking, sun rays are parallel rays. They must fall directly wherever we are. Whereas at Sian, it is falling directly on the head. Whereas in Alexandria, it is making an angle of 7.2 degrees. In that case, it has to be due to the circumference of the earth. So using that, we can find out what is the radius of the earth. So that was his idea. And what he has done, see, you can see the map of Alexandria and Sian. Here it is. So you can see at one place the sun rays, for example, Sian, the sun rays are directly falling. Whereas here, the same sun rays, they are making an angle of 7.2 degrees. So here it is 7.2 degrees that we are extending to the center of the earth. So if we are extending to the center of the earth, this is the radius of the earth. If you are taking that to be A, the entire circle, it is covering 360 degrees that I have written here. 360 degrees, and this angle, it is only 7.2 degrees, alternate angles. So if this is 7.2 degrees, this too must be 7.2 degrees. Therefore, 7.2 degrees divided with 360 degrees, that is equal to the distance corresponding to 7.22 degrees is only 800 kilometers. So that I have written 800 kilometers divided by, I do not know what the entire distance is. That must be equal to 2 pi a. So that 2 pi a, that I have written it as x kilometers. And what is this x kilometers? Very simply, very easily, that can be found out. So that has been found out as 40,000 kilometers. So this Eratosthenes, he has found out so many years, nearly 3,000 years back, he has found out this. And very recently, after the invent of satellites and other things, we have found out that the circumference of the earth is almost equal to 40,000 kilometers. Only some 30 years back, we have found out using this. So that is the power of mathematical model. Eratosthenes, using a very simple concept, using a very simple mathematical model, he has found out the circumference of the earth very easily. Hence, the mathematical models, they are not only making our efforts easier, also they are making our expenditure very less. So the first jetliner to be digitally designed, it was pre-assembled on computer, eliminating the need for costly full-scale mock-up. So computational modeling, it has improved the quality of the work and reduces changes, errors, and rework. Hence, it is not necessary that you have to do it now. Even the rocket designing, how it will be working, all those things you can do, you can model using lot of computer software. One of the example is you can go with the Creo, or you can go with even rocketry. There is one software. So using that, you can check what is the velocity of that particular vehicle which you are designing. What will be the drag? What will be the lift? What will be the effect of the turbulence on that? So what will be the effect of wind speed on that particular jetliner? All those things can be now very easily modeled, and they can be studied, and after that the entire aircraft can be designed. The one of the most important area where mathematical model is playing a crucial role is climate modeling. And in climate modeling, you can never say you you cannot wait for after 6 months how the rain will be. That can in no way else it can be predicted except using a mathematical model. So in mathematical model, today's mathematical model, we are using a 16 parameter system. What we are doing is to find out whether tomorrow there will be a rain or not. We will check what was the status of the rain status last year, and what is the pressure today, what is the temperature today, what is the humidity, and what is the temperature of the last year. What is the El Nino? Is there any mountain present in that region? So many parameters are taken into account, and the mathematical equations are formed, and those mathematical equations are solved using supercomputers, and from that we are giving the predictions. And this is done by many IMD in India, and most of the time their predictions are correct. It is because they are using the mathematical concepts. And one of I personally witnessed, they are using Newton-Raphson method to solve certain equations. That has been depicted, and those who are visiting that IMD, you can also see everywhere it is depicted. So mathematical concepts are used. Only mathematical concepts are used in climate modeling. So what is your mathematical modeling process? So first thing is we take a real life situation. So it could be a prediction of weather and climate, or it could be a prediction of how much demand will be there, and it could be a prediction of what will be the impact of the lowering uh, taxes, then or how the economics of the nation can be affected. So all these things you can just take as a real world problem. And when you are taking real world problem, it is involving too many parameters. It is involving too many unknowns. So sometimes it cannot be mathematically tractable. It may not be easier to solve that equation. So whenever we are having a real world problem, we simplify them, and we are bringing them to the working model. See, for example, when you are considering um, climate modeling, you can always assume that the air is not a viscous fluid, but it is a compressible fluid. So, like that, you can make certain assumptions. And when you are dealing with water, you can assume that it is an ideal fluid. That is, it is having a zero viscosity and it is incompressible. That way, you can assume. So, certain assumptions are made to simplify the real world problem to bring it into a working model. So when you have brought it into a working model, we are converting that into a mathematical model. So what is one particular symbol represents? X represents what? Y represents what? And is the time element is there? So T will represent time. Like that, we are using that. And is it a continuous model? Is it a discrete model? And what is the change in which variable is bringing out a change in another variable? So all these things we will be discussing, and we will be formulating either a system of algebraic equations or transcendental equations or differential equations. So we will be bringing it all the required equations, and we will try to come out with a mathematical model. Once you have brought it into your mathematical model, again, that mathematical model need not be solved. We may not be having adequate tools to solve the mathematical equations. In that case only, we again go for approximations and assumptions. We make certain approximations and assumptions, and we do convert them into the computational models. And when we are going for a computational model, then we make some simulations to get results and conclusions. And once the results and conclusions are got, they will be in terms of x, y, t, etc. So they have to be interpreted into the real world variables. So when you are, whether it is representing a pressure or a temperature or a density or some other variable, so all those things we will be doing, and we will be converting into the real world situation. And we will check our model whether this is correct. So என்னுடைய prediction, whether it is coinciding with the existing data. So we try to validate the results we have got. And once the validation is not accurate, then what we do is we try to improve. So the simplifications which we have brought in, those simplifications we try to make it a little more harder, or we do different kind of simplifications, and again we go for another working model, and then we will represent that as a mathematical model. Then we will convert it into a computational model. Then we will come down to results and conclusions, and again we will interpret it to the real world problem, and again we will check with the existing data and validate. So this way it is a cyclic process, and the mathematical modeling is not one time process. It keeps on improving on the previous model. So we have a hierarchy of mathematical models. So again, this mathematical models, you can classify them based on many things. So one of the thing is you can classify them based on subject matters. Whether it is a mathematical model in physics, is it a mathematical model for chemistry, mathematical model for biology, mathematical model for economics, mathematical model for engineering. Likewise, depending upon the subject matter, you can do it. And again, the mathematical model can again be classified as per the mathematical techniques used. Whether you are using calculus, whether you are using algebra, whether your trigonometrical concepts are used. Based on the mathematical technique, you can classify the mathematical model. And what is the purpose? Are you using that just to get an information, or are you defining a mathematical model to get some insight, or are you defining a mathematical model to control a situation, or do you want to predict something? So depending upon the purpose also, you can classify the mathematical model. And also the nature, whether the variables involved, the equations involved are the deterministic or stochastic, or linear or non-linear, depending upon the nature of this system of equations and the variables. That way also you can classify the mathematical model. Okay. So some characteristics of the mathematical model is it should be a realistic model. See, when I say a mathematical model should be realistic, what I mean by that, see, suppose for example, I want to build a house or a room. When I want to build a room, I say the room can be built if 10 people are used to construct the building, 10 days it will take. Then, as I'm curious, what if I'm providing you 20 men to work? So when 20 men are given to work, then automatically what we will say, mathematically, within 5 days, we can complete it. So, okay, suppose if I'm giving you 40 men, then 2.5 days. If I'm giving you 80 men, so this is all mathematically possible. If 80 men are given, how many days it will take? 1.5 days. Then if I'm giving you 160 or 200 men, maybe it is in few hours, 6 hours. Then if I give you still more, 5,000 men if I am giving, then is it possible to complete the room within half an hour? Yes, it is possible mathematically. It is mathematically possible. But in real life, it is not at all possible, because we have in our mathematical model, what we have done is a person, how much time he will take to construct the building or construct the house, that we have taken into account, whereas which we have not taken into account is the moving space, working space, curing time. So many variables we have left out. That is, we have simplified it by leaving out those parameters. So hence, realism of the models, it has to be considered when you are defining a mathematical model. And as I said, hierarchy of model, it is not one way. Always you will keep on improving the models. Therefore, model number 1, it will lead to model number 2, that will lead to model number 3. Like that, it will keep on moving. Right? Similarly, relative precisions. See, sometimes if you are dealing with economic vectors, 2-digit precision will be enough, because 100 pies that will do. So 50 pies, 60 pies, 75 pies, that is enough. But when you are dealing with a missile, then microseconds, 0.0000, so 5 seconds, that is also important. When an enemy missile is coming into our territory, identification, there the precision is more important. There you cannot have a 2-digit accuracy. So So relative precision, that also depends upon the situation which you are dealing with. Then a model should lead to new experiments. So whatever you are doing, that must give you some insights to take up a future venture or some other new experiment. For example, it is a very, very simple example which everybody can understand. So I'll take up this. How much space is inside this cardboard box? That is, I want to find out what is the volume of this box. L into W into H. Right? So we know the three measurements, H, W, and L, and the formula for the volume of a cuboid is H into W into L. Whereas I want to go with a very precise calculation. So when I go for a precise calculation, I must consider the thickness of the cardboard. So if the thickness of the cardboard is H, then the length is not L. Instead, the length is L minus 2 into thickness, 2T. Similarly, the width is also not just W, it is W minus 2T. H is not just H, it is H minus 2T. So now, if I am considering the thickness of the cardboard, then the inside volume now reduces to this. H minus 2T into W minus 2T into L minus 2T. Okay, I'm happy. So instead of volume H into W into L, now I have a different volume H minus 2T into W minus 2T into L minus 2T. Now this is leading to a new experiment because the cardboard is T thickness and all measurements are outside the box. How much space is inside, that we have done. Now my company is using 200 into 300 into 400 mm size boxes and the cardboard is 5 mm thick. Suppose somebody is suggesting that instead of 5 mm, suppose if we are going for 4 mm cardboard, how much better is that? So that is the new experimentation. So in that new experimentation, we find out what is the current volume and what is the new volume. So if the thickness of the volume is reduced, then we see there is a change of 2% increase in the volume. Okay. Okay. Now again, another example in the real life situation, I would like to give it to you. It is a model. She was found dead at the bottom of the gap at Sydney's, Australia in 1995. So till 1997, at University of Sydney, a physicist, Rod Cross, he was asked to give a report about that, whether it could be a suicide or it could be a murder. In 1998, it was said that it is a suicide, right? So this is Bain. So this is a model who was found dead in Australia, and it is her boyfriend Wood, and this is a physicist, University of Sydney professor, physics professor. Now what is happening? The police was asking for a report from this person, and they have found out that she should have committed suicide, and they have closed the file. After closing the file, they wanted to tie up all the loose ends. So whatever they have initiated, everything they have to collect the report and they have to close the file, and the documentation has to be completed. And for that particular purpose, they went and found out the report. They asked for the report from the physicist. And in 2003, they have contacted him and he said, this Caroline, she could not have slipped or jumped. So it must be a murder. That was the verdict given by the physicist using a mathematical concept. And based on that, in 2006, her boyfriend, he got arrested in London, and eventually he was sentenced to 17 years in jail with a non-parole period of 13 years. So what is the mathematical concept in this, whether to discuss whether it is a suicide or it is a murder? See, this is the scene of the crime, and this is the place where the body of the model was found out. And as for the mathematical concept, it is a projectile. So if somebody is throwing it, it will go somewhere. Whereas if the model herself, she comes running down and she jumps over the hill, then this is the maximum range. So she should have found, her body should have been found only at this position, whereas the body was found here. So this, as per the projectile concept, this cannot be the maximum length. So it is more than that. So this is possible only the body was thrown off. And that was the result given by Rod. And based on that, the boyfriend was got into this. And another model which I would like to show you is this. The model that was used in a war. Normally, it is the very cool experiment which all of us, we have done it. Focusing this and all the sun parallel rays, they will be focused at one point, and using that one point, the entire paper will got burned, right? And now, the same concept, it has been used by a different mathematician and in a different manner. All conic sections, they possess a mirror property. In case of, and especially in case of parabola, the light emitted from a source located at the focus of a parabola and reflected off its inner surface travels along a straight line parallel to the axis of the parabola. See? Yeah. So this was used by Archimedes. And here, what we are doing is, from here, if you are drawing a line and it is going like this, then all these will make the same angles. This is the concept, basically. And the concept Archimedes used was in the reverse. In the reverse order, all the parallel rays, when they fall upon a parabolic mirror, they must get reflected, and all of them, they should go to this focal point. And at this point, if something is there, it will get burned, right? So using this concept, he has burned the enemy ship. And most of another mathematical model that is used in day-to-day life is elliptic sound galleries. Most of the sound galleries, if you look into it, they will be using the elliptical shape. If the water surface is disturbed at one focus of an elliptical water tank, the circular waves created by that disturbance, after being reflected by the walls, will converge simultaneously to a single point, that is second focus. That is, you will have one ray going on that will fall on the wall of the elliptical, it will fall on the elliptical wall, get reflected, and it will pass through the second focus. So the sound waves are reflected in a similar way. So in a large elliptical room, a person standing at one focus can hear a person standing at the other focus remarkably well. Okay? So using that concept only, all the auditoriums, they normally either the building or the stages are made using the elliptical structures. And you can see the mathematical concepts used in so many buildings. You can see parabolic hyperboloids, and here you can see this. It is 591 feet wall and 41 floors skyscraper. And this uses this concept here, the tapered end, to avoid turbulence inside the building. So to avoid the turbulences, this mathematical concepts, this design architect has suggested that only this has to be used. And you can see a Buddhist temple in China. This is nothing but one place you start, you will end up at the last end. And all of you, most of you would have recognized what this shape is. It is known as Mobius band. And this Mobius band is used in every escalators. Wherever, whichever mall you are going, all the escalators are using this Mobius band. And this is a building constructed purely with the tetrahedrons. So, I would like to quote Srinivasa Ramanujam. he said, an equation for me has no meaning unless it expresses a thought of God. That means what we say is, what he meant was, every equation that we are dealing with, it will represent a real life situation or a physical situation. Similarly, every physical situation that will be represented by an equation. Vice versa, every equation represents a physical situation. Similarly, every physical situation can be represented by an equation. See, from the simplest example, if you want, you can just look into this. Y double dash plus 4y equal to 0. This is a very, very simple problem which we teach the children at the first year. Nowadays, even in +1, we are teaching this. So when such a problem is given, y double dash plus 4y equal to 0, then we teach them, you write the complementary function, m square plus 4 is equal to 0, or m square is equal to -4, m is equal to plus or minus 2i. Then the solution is y is equal to a into cos 2x plus b into sin 2x. That's all. So this is what we teach in every class, every calculus class, very basic fundamental equation. But what is the representation of that equation? It represents the simple harmonic oscillator, spring mass system, even simple harmonic motion. Everything is represented by such an equation, y double dash plus 4y equal to 0. You may wonder how. See, because here the net force F for all these systems, F is equal to minus k into x. But what is your F? F is mass into acceleration. And mass into acceleration, what is your acceleration? It is nothing but d square x by dt square. So d square x by dt square, that is equal to minus k by m into x, or in other words, it is x double dash plus a constant into x is equal to 0, which is nothing but a similar equation to your y double dash plus 4y is equal to 0. Hence, this motion, it is represented by this equation. This motion is represented by this equation. This motion, this is also represented by this equation. So, which problem we can model? Using a mathematical model, anything can be modeled using a mathematical equation. Everything can be modeled. One of the best example is your 7 bridges problem. And the 7 bridges, all of us, we are very, very familiar with it. And we are having certain regions, they are connected by 7 bridges. And the people of that region, they wanted to cross all the bridges with one particular concept, that none of the bridges must be left out and all the bridges must be crossed only once. So reverse movement is not allowed. Then they were doing this for a longer period, and it has become talk of the town once because they could not find out a solution for that. That came to the knowledge of the Euler, one of the greatest and finest mathematician, who has an embodiment of a mathematics lover, and one of the example which each and every one of us has to emulate upon. And that person, he was half blind and he was at a very old age, nearly he has crossed 70 plus at that time. And at that time he came across this problem and he was drawing a picture, simple concepts, and he has proved that this problem will never have a solution. So it is the mathematical representation of this problem. Nowadays we call it in graph theory, these are all the vertices and edges. And this graph theory is used in communication networks and traffic flow problems. And this problem, this representation is the first proven theorem of graph theory, and it is the basis for topology also. So it is the first paper in many ways. And similarly, you can consider this Knight's Tour. It's a very, very known problem to everybody. All the children will be playing this game. That is, you have to trace the horse movement in such a manner that the horse should visit all the squares and it should not leave out any one of these squares, but it should cover each and every square. That is the case, right? And here in 8x8 board, you can see how this horse is moving out. The knight is traveling, and this is Hamiltonian path problem in graph theory. And the solution is given here. The problem of finding a closed Knight's tour is known as Hamiltonian cycle problem, and this is a crucial problem. This problem is forming the basis for neural networks. And I'll come down to a very simple, well-known prey-predator problems. In prey-predator problem, what they will be doing is, they will be having a prey and we will be having a predator, and this will eat this prey. This is the way. So I'll just consider X and Y represent the population of the prey and the predator. Therefore, any change in the prey population, that is change in the prey population, is given by dx by dt. This dx by dt is proportional to the existing population. Therefore, it is alpha into x. Then whenever it comes into contact, whenever it interacts with the predator, that is interaction is multiplication, therefore x into y. Whenever there is a x into y, there is going to be a decrease in the prey population. Therefore, it is alpha x minus beta into xy. Similarly, you consider this predator population. Predator population, again change in the predator population is given by dy by dt, and that is equal to, in the absence of a prey, there will be a decline in the, there will be a decrease in the predator population. Therefore, I am associating a minus sign. So it is minus gamma into y, and whenever this predator is meeting a prey, then there will be an increase in the predator population. Therefore, there is a plus sign. So plus delta into xy. So dy by dt is equal to minus y into gamma minus delta y. So when you solve this equation, you get its periodical solutions, and these can be interpreted, and we find out that there is an impossibility of predator extinction. Okay, the same model can be used for human population. Yes, the human population, there is not going to be any predator, so there is no need for having another variable. So what I will do is, I will just take the rate of growth of the population to be dp by dt. It is going to be proportional to the existing population. If there is 100 people in one place, then the next year there will be 110 people, because there will be some reproduction. And after that, this 110 people, they will be further reproducing. So next year there may be 122. So like that it keeps moving. Therefore, dp by dt is proportional to p. That proportionality, constant of proportionality, I will take it as k. So dp by dt is equal to k into p. Now this is a very simple mathematical problem which can be easily solved. So dp by p is equal to k into dt. So on integration, we get T of t is equal to some arbitrary constant into e power kt. Now this solution is c and k. These two are distinct constants. These are all the parameters of this system. Now I'll go with this. So when I'm having this, how to find out the c and k? There will be some pre-existing values based on each country. So in India, we are taking census every 10 years. So when we are taking every 10 years, we will be having values in 1981, we will be having 1991, and 2001, we will be having certain values. So I know the population P of P at when the value of P is equal to 1981. Similarly, I know what is the value of P when T is equal to 1991. So using those two equations, I can always determine what is my C and K for India. In the same manner, for Pakistan, I can find out what is C and K. For Bangladesh, I can find out what is C and K. Similarly, for Nigeria, USA, UK. So wherever, whatever is the country, there will be pre-available data. And based on those pre-available data, I can find out C and K. So this C and K parameters, they will keep on changing from country to country. See, it is a very simple mathematical model, and you see how it gives you the graph. So when I'm saying this is the, what are the most populous countries, as per my expression, as per my C and K, I'm calculating and I'm just um, writing them in the most populous order, right? In that case, you can see this can be very easily interpreted or simulated for more than 60 years, 70 years, 100 years, or even any number of years. That interpretation can be, or that calculation can be done. And you can see this China is on top till 2007, 8, 17, 19, and suddenly India is coming on top. And after 2027 and 28, the India will come on top. Similarly, you see the growth of Nigeria. Nigeria, even in 1996, it is somewhere at the bottom, but the Nigerian population is growing, and you can see Nigeria is ending up to in 2060, Nigeria is going to be the third populous country. So this is the prediction what we have done, and this can be very easily done using a mathematical model. And another mathematical model is this. See, you can see a dog is drinking the water. And when it is, you can see the dog, the tongue, when it is curled, then that water is making a splash. This curve structure is making a splash. That concept has been used in Shanghai Airport. So you can see this 9-story height artificial waterfalls, it has been constructed based on this concept. So, okay, and here how these are considered. So, இது வந்து almost like to put it in mathematical terms, it is like a huge glass bagel. You complete with the hole in the middle. So it is through this hole that water will fall 9 stories, dropping into what looks like a second waterfall that begins at ground level. So here, mathematical concepts, fluid dynamic concepts, plus structural engineering is also required. So when these 3 subjects are put together, you can create an artificial waterfalls. And is there nothing wrong in having artificial waterfalls? Yes, there is a difficulty, there is some kind of problem. What it is, when this entire waterfalls, this is a natural waterfall and this is an artificial one. When this artificial waterfall is coming down, what is it takes out all the air around it and making the entire airport, it makes the entire airport little humid. So just 5 minutes, I will wind up. So in the entire airport, it will be making it very humid. Therefore, what we are doing is we have to plant some kind of trees, and what is how many plants has to be put in that, and all those the concepts, it has to be done only with the help of mathematics and biological sciences. So when I say mathematical modeling is great, the next question that comes to our mind is, don't mathematical models fail? Yes, they do. When mathematical models fail, then what happens? That is an example given by this Tacoma bridges. This Tacoma bridges, even now it is existing. That was opened in the year 1940, and at that year, it is a twin bridge. It is a suspension bridge based on the concept of catenary. So catenary is again what we teach in the second UG course. So that catenary concept is used here, and it is a suspension bridge, and it is the 3rd longest suspension bridge in the world in terms of main span length. The original Tacoma Bridge was opened in 1940, and what happened? It broke down in the November 7th, 1940. And what is the reason? The contributing factor was its solid size. They did not allow wind to pass through the bridge deck. So here, to make it very simple, the mathematical design, it has not taken into consideration the singular point. And when the singular point has been neglected, there has been a infinity solution and which has thrown the bridge out. So it's a failure. Because of it, it has boosted a research in the field of bridge aerodynamics. And nowadays, all the designs in the world are built based on these concepts. So with this, I'm coming to the end of this session. In conclusion, what we can do is everything can be modeled using mathematical concepts, and every mathematical concepts that will represent a real life situation. And it is up to us to look into how well we have to go with the concepts and how we have to model it and where we stand. That is up to us to do the research. So with this, I'll close. If any questions, I'll be ready to answer.
Thank you so much, ma'am, for the wonderful presentation. Dear participants, if you have any queries, kindly post it in the chat box or you can unmute and ask.
I think,
Yes, ma'am, I think there are no questions.
yeah, I thank the organizers for having given me this opportunity, and I'm congratulating you for the excellent work done. Thank you very much.
Thank you so much, ma'am.
Ma'am.
Yes, ma'am.
Thank you, ma'am. Thank you, ma'am, for your informative and interesting presentation. Now I invite Dr. J. Martina Jensi, Assistant Professor, to propose a vote of thanks.
Yeah, very good afternoon, one and all present here. It's my great pleasure to propose the vote of thanks on this successful fifth day of our 6 days FDP. And first and foremost, I thank the Lord Almighty for His abundant blessings. And I express my sincere gratitude to our Honorary Secretary, Thiru APCV Chokalingam, and our beloved Principal, Dr. C. Veerabahu, for their constant support and encouragement. And my sincere gratitude to Dr. C. Deva Manoharan, Head of the Department of Mathematics, for his unwavering support and guidance in organizing this event. And my special thanks to our resource person, Dr. K.Sumathi, Associate Professor and Head of Department of Mathematics, PSGR Krishnammal College for Women, Coimbatore. Thank you, ma'am, for sharing your expertise with us. Really, it is very interesting and informative. And thank you for demonstrating the power and beauty of mathematical modeling. Actually, the presentation was a perfect blend of information and inspiration, ma'am. And we are thankful for that experience. Thank you so much, ma'am. And I would like to extend my heartfelt thanks to all the participants who joined us via Google Meet and YouTube Live for your energetic engagement and active participation. Your enthusiasm has made this event a resounding success, and we are grateful for your involvement. So, once again, I thank one and all present here. Thank you all, and we will post the feedback link in the chat box. Participants, kindly